Hello students, welcome to today's session. Today we will going to discuss about point processing, then spatial filtering basics and intensity transformation. Okay, so there are two different domains, spatial domain and frequency domain. Okay, so now let's discuss more about operations in spatial domain. So in spatial domains, we act on directly on pixel values, and general form of operation is like g of xy is equal to t of f of x comma y. Okay, where t is operator defined on f over neighborhood pixel x comma y. Okay, point x comma y. Okay, students. So it requires less resources and it is computationally more efficient. Okay. Now let's see what is spatial filtering. Okay, so spatial filtering means it involves operations for entire image, and whereas operation only takes place at point of interest. Okay, it's like there is one point x comma y. The operation takes place only in that point's neighborhood. Okay, so there is one predefined operation function called as spatial filter. Okay. So spatial filter has different types, like it been classified into spatial mask, kernel, template, window, etc. Okay. So we will discuss this one by one when we solve numericals of DIP. Now let's see what is point processing. Okay, so point processing, like here the pixel one by one of size is the smallest neighborhood. Okay, G depends on the value of f at x comma y. Okay, see we have the value of intensity transformation function as s is equal to t of r. Okay, where s and r represent intensity value of g and f at point x comma y. Okay, this is called gray level function or a mapping function. Okay, now observe these two different intensity transformation function. The first is contrast stretching function, other is threshold function. See the exponential increase in the value of s, okay, in the first graph, and it is increasing stable in second graph of thresholding. Okay, here the value of threshold is over here. Okay, and here it is increasing exponentially. So now we will discuss about some intensity transformation functions. So students, always remember T is the transformation that maps a pixel value R into pixel value S. Okay, R is the source and S is the destination. So basically there are three types of transformation: linear, logarithmic, power law. Okay, so in linear transformation we can make image negative. See, the image negative of image lies in the intensity level 0 to L minus 1. Okay, and S is equal to L minus 1 minus R. Okay, here means the color becomes opposite. Whatever is the blackish part, it will become white, and whitish part is becoming black. Okay, second is log transformation. Here the changes occur with respect to logarithmic function. S is equal to C log of 1 plus R. Okay, where C is constant and value of R is greater than or equal to 0. Okay, now here a narrow range of low intensity values in input to wider range output is made. Okay, so the compressed value of dynamic range images or dynamic range of images with large variations can be seen in pixel value. Okay, see this log transformation example. So Fourier spectrum is a log transformation example. See here, the spot was seen over here, but if we apply Fourier spectrum to it, like it is a Fourier transform, we get this resultant image. Okay, we have studied this. Next is power law or gamma transformation. Here, the power here the resultant image changes with respect to power. Okay, power of R. Okay, so S is equal to C R raised to gamma. Okay, so and C and gamma are positive constants. So power law curve with fractional values of gamma will map a narrow range of dark input values to a wider range of output values. Okay, we will see this diagrammatically in the upcoming slide. This is the power law transformation curve. Okay, see students, there is a exponential increasing and decreasing graphs. Okay, according to the changing values of gamma. Okay, like gamma is varying from 0.04 to gamma is equal to 25. Okay, this is how there is variation of transformation curve using gamma function. Now let's see where we can use gamma correction. In some devices, it is used for image capture, display, and printing according to the power law. Okay, like CRT devices where we use cathode ray tube, they have intensity to voltage response. Okay, students. So it is used over there. So for this, gamma correction can be calculated using S is equal to R to the power 1 upon 2.5. Okay, so that is R to the power 0.4. Let's see using image. See, after gamma correction, we are getting this resultant image. Okay, see the difference between this upper and this below image. It is quite more transparent and is very totally corrected image as respect to the previous given image. Okay, it is also useful in MRI. Okay, see this MRI image of this bone. After gamma correction, we are getting appropriate value of this bone. See, this is aerial example, image taken by NASA, Space Agency of USA. So, in the first image, the image is entirely cloudy. Okay, we can correct this image using gamma correction technique. Okay, image transformation, image intensity transformation using gamma correction, and get the clear image with clear object boundaries. So piecewise linear transformation is another segment. So examples for this include contrast stretching, intensity level slicing, and plane slicing. Contrast stretching, like it means like expanding the range of intensity levels. Okay, see, this is the original image. Okay, if we change, we will get some image like this. Okay, it is completely binary image. Okay, intensity level slicing, it means like see, we are given some specific range of intensities, so we have to highlight the intensity that is of our area, which is in our area of our interest. Okay, so the graph variation is shown as below. Okay, there are two main approaches for that. First, we can either set all pixel values with range of interest, like we have some area of interest and interest to one value, white. Okay, like make some value white and all others value as dark. Okay, it will produce binary image, or otherwise brighten or darken pixel values in area of interest and leave all other things unchanged. Okay, so let's see, we have such one example of that. See this image of this figure. See here in the middle image, the area of interest. So this shape is enlightened and other is made dark. Okay. So which is the required image, with required object, that is made the white and others are made dark. Okay. Then bit plane slicing, like we are having every pixel value which is composed of some bits. Okay, like a pixel in 256 grayscale level is composed of 8 bits. Okay, like one byte is 8 bit. So every pixel in this 256 level grayscale image is comprised of 8 bits. So 8 bit means 1 byte. Okay, so students, in bit plane slicing we can highlight the contribution made to total images by specific bits. Okay, for example, we can take any image, like we want to display that image, and that shows contribution of specific bit plane. Okay, like there are numerous number of bit planes present in every image, but we are bothered about only specific area of the total image plane. Let's see this image of an American dollar. We can see the image. Okay, like if we apply bit plane slicing, we can get a binary image also. Okay, so we can get different images according to the different reference bit plane we are using it. Okay, so see, this is the final image that we get. So students, now we will see what is the use of bit plane slicing. So it is used for determining number of bit necessary for quantization of image. Then bit plane slicing is also used for image compression. If the image size is extremely large, we can reduce it without harnessing the image quality. We can compress it. Okay. For this, bit plane slicing is used. Thank you, students. Today we have studied about image transformation techniques, then point processing, and etc. Spatial filter, and how spatial filtering is different from frequency domain filtering. We have observed this. Okay, I hope all of you enjoyed today's session. If you have any doubt, you can comment in the chat box. Thank you.